All right, welcome to lesson 10-2. In this lesson, we are going to look at some operations on vectors, and then we're going to look at another form for writing them. So starting out, this is just a little review of what we did in the previous lesson. It says given vector u with horizontal component of 6, vertical component of -3, find the magnitude, right? Remember this symbol means magnitude, as both an exact value and as a decimal rounded to the nearest thousandth. All right, so that should be pretty easy to do. Remember, if vector u has a horizontal component of 6 and a vertical component of -3, that means it's got to be starting going to the right and down in this direction. So our vector u would look like that. Okay, so if we want to figure out what the magnitude is, right, we can just use that formula because we're going to the right 6 and down -3. So we'll take it there. You can call it Pythagorean theorem or just think of it as we're going to take the square root of 6 squared plus -3 squared, which ends up being square root of 36 plus 9, or the square root of 45, which in exact form would be 3 radical 5. And then our decimal approximation would be about 6.708. And that's it. All right, let's move on. So, vector operations. Okay, so this letter A says draw vector B. So we're going to start at this initial point. We're going to draw vector B. So we're going to go to the right 3 and up 1. Just like that. That is our vector B. Okay, now it says draw B plus B. Well, if we went to the right 3 and up 1 with vector B, we'll just do it from the end there, right? Remember when we add them, we just continue on from that terminal point. So we'll go to the right 3 and up 1. We'll draw in the second one there. So that is also a vector B. And if you think about putting it all together, that is simply B plus B. So it says, what is another name for B plus B? Well, let's just simplify it and call it 2B. Now write this vector in component form. Okay, so let's just take it and we'll start here and we'll count over 1, 2, 3, 4, 5, 6, right? So we've gone 6 to the right and then we've gone up 1, 2. So our component form for our B plus B would be 6, 2. Right, so we could even write that, right? So this is like vector 2b would be equal to 6, 2. So now it asks us to find the magnitude of both b and 2b. All right, well, that's no problem. Let's do that. Remember, magnitude is just the length. So if we wanted to find the length of vector b, I'm just going to draw it a little bigger here. Right, this is our vector B. So we went to the right 3 and we went up 1. So we'll take it here and we'll say, all right, well, we're going to do the magnitude of vector B is going to be the square root of 3 squared plus 1 squared, which is going to be the square root of 10. So the magnitude of vector B is 10. And if we look at the second one, right, we know on this one, this is like 2b. Okay, so with our vector 2b, we were going to say its horizontal component was 6, and its vertical component there was 2. So we could say that the magnitude of 2b would equal the square root of 6 squared plus 2 squared, which is going to be 36 plus 4, or 40. And if we simplify that down, that should be what, 2 radical 10? So if you look at those numbers closely, right? So for vector B, right, we had our magnitude was just radical 10, right? And then we took our 2B, right? And we now have a magnitude of 2 radical 10. So by multiplying by something in front, right, all we're doing here is really multiplying our magnitude by that same number. Okay, so that 2 in this case, right, this 2 is what we refer to as a scalar. Okay, so it is a scalar. And if you think back, scalar, you've seen them before. You probably called them scale factors in geometry and algebra 2, right? So it's just increasing the size of everything, but it's not really changing much else about it. So let's jump into this next part here. It says scalar multiplication of vectors. So when we have these scalars, right, and you'll see on the side here, you've got vector u being multiplied by different numbers here, and we'll talk about how it affects this vector. So let's start out with vector u. It's got a horizontal component of -1 and a vertical component of -2. So if we just took that and drew that in here, right, it would go left 1 and down 2. So this would be like our vector u. Okay, so what we'll see here is if we took 3 and we multiplied it by u, okay, if we look back at that previous slide here, right, originally on this one we had vector b, right, which was 3, 1, and as soon as we inserted that 2 and multiplied 2 times b, we multiplied each of these values by 2 in order to get our 6 and our 2. So our new component form for 3u would be -1 times 3 would be -3, and then -2 times 3 would be -6. Okay, then let's go ahead here and, you know what, let's draw that one in first. Let's look at that one. So we have -3, -6. So as I go to draw that, let's try it like right here. Okay, so let's start there. We're going to go the left 3, but we're going to go down 1, 2, 3, 4, 5. And this one doesn't actually fit on there, but just do your best. All right, we'll take it, we'll draw it in there. So this is our 3u. Okay, now let's look at 1/2 u, right? So we're going to take -1, multiply it by half, and -2 and multiply it by half. So we're going to have half of -1 would be a -1/2, and half of -2 would be a -1. So let's draw that in, right? We'll start up here. Let's go half back and then down 1. So probably something like that. This is 1/2 u. Let's do 0 times u, right? So if we did 0 times our horizontal component would be 0. And the same thing with our vertical component. So when we multiply our vector by 0, it still exists. I mean, we still have this point right here. This would be like our 0u, right? It just doesn't really have any direction or magnitude beyond that. Okay, and then we got one more. We got a -u. Well, if we take a -u, right, we're going to multiply -1 times a -1, we get +1, and then we get +2. So if we're going to draw this one, it's got to go to the right one and up 2. So if I start here, right one and up 2, right, it's going this way. So let's kind of examine those. And it asks, what do positive scalars change about vectors? Well, notice all of these were multiplied by, well, that was our initial one, but everything was multiplied by a positive scalar right there. So it looks like it just changes the magnitude, but the direction does not change. So it changes the magnitude or length, but it does not change the direction. And then that next part asks, what relationship do that negative u and our positive u, like what's happening there when we multiply by the negative? Well, it looks like it's going to make it go the opposite direction. All right, vector u goes down to the left, but vector negative u goes up to the right. All right, next thing we'll talk about are unit vectors. Okay, so you've talked about unit stuff in the past, like the unit circle. We call it the unit circle because it has a radius of 1 unit. And very similarly, a unit vector is just a vector with a magnitude of 1. So you'll see here we have a couple unit vectors, and we'll use vector I and vector j to help us write out our new vector form here in just a moment. Okay, so you'll see that vector I, vector I is defined by a horizontal component of 1 and a vertical component of 0. So you see here is vector I. And then we've got vector j, which is defined as 0 for its horizontal component and 1 for its vertical component, right? So that one just goes up 1 like that. Those are both unit vectors because their magnitudes are 1. So now they're going to ask us to find and then draw vector 2i. Well, what are the horizontal and vertical components going to be for 2i, right? We're going to take what we have up here and we're going to multiply each of them by 2. So that should be 2, 0. So we'll draw that in. Let's draw it like just right here would be fine. And go to the right 2, just like that. That's 2i. And then they want us to do 3j. Okay, so if we take everything here and multiply it by 3, we'd have 0, 3. So that one would look something like this. It's going to go 0 to the left and right and up 3 units. So that's 3j. Now they want us to find 2i plus 3j. Well, remember, we can do that algebraically if we focus on what we've got right here. Right, 2i plus 3j should come from adding our horizontal and vertical components. So in this case, 2 plus 0 should give us 2, and 0 plus 3 should give us 3, so it looks like our horizontal and vertical components should be 2 and 3. Which is kind of neat because you can kind of see here, well, 2, 2, 3, 3. Okay, because we know I and j just had magnitudes of 1 on each of those. If we were to draw that in, right, we would have to start maybe down here. We go to the right 2, and then we would go up 3 units, right? And our actual resultant vector would be this one. We'd have 2, we'd have 3. So this would be our 2i plus 3j. So it says any vector can be written in either component form or unit vector form, which we also call ij form. So what you're seeing right now here is this is actually a form for writing vectors. Okay, so this is what we refer to as the ij form, or you could call it the unit vector form. Okay, they mean the same thing. Okay, and so they can also be written in their component form, right? This is the component form. And over here is what we refer to as the unit vector, or our ij form. Okay, so both of those mean the same thing. So let's look at that a little bit. It says write the vector 6, negative 2 in ij form. Okay, so when we think about it here, remember I was describing our horizontal components, and then j was going to be kind of describing our vertical components. So when we look to do this, you should end up with your 6i, and then you could say plus a negative 2j. right? Or we could write that as, right, just 6i minus 2j. That's probably going to be the more popular one there, right? Instead of adding the plus minus thing like over here. And then it's really easy to go the other way too, right? Write the vector negative I plus 3j in component form. So let's just look at what are the coefficients on the I and the j, and we know that those are going to go into those pointed parentheses, right? So this would be negative 1 for our horizontal component, and then positive 3 for our vertical component. Find the magnitude and direction of negative 6i plus 13j. So we start out there, that's our unit vector form. Let's write it as a component form. That would be negative 6, 13. So left 6 and up 13. We'll draw a little picture. So left 6 and up 13. It's not going to be drawn to scale. I know my batteries are getting low, so I'm just trying to make sure I get through it. But here is the actual vector here, right? The blue one I'm drawing in is the actual vector. So it says on this one, we've got negative 6 and 13. So to get our magnitude, right, we're going to do the square root of negative 6 squared plus 13 squared, which is going to be, what, 36 plus 169, which I believe is 205. And I don't think we really gave this a name, but we'll say, the magnitude here is going to equal the square root of 205. And I guess we'll go ahead and get the decimal form, right? Second square root 205, 14.318. And then to get the direction, right, we're going to take it, we're going to think about this angle that opens from here to here, right? That's our theta. So let's find the reference angle inside of here, and then we can come up with it. So we know that we would end up with the tangent of theta is going to equal opposite over adjacent. And in this case, I'm going to go ahead and just keep it positive so I can find the reference angle. Remember, inverse tangent does not live in quadrant 2, so it's probably going to be easier to do this way. So we'll say theta is going to equal the inverse tangent of 13 over 6. We'll calculate that. $65.225. And actually, this isn't theta, but we should call this x. Sorry about that. So x should be, what did I just say, 65.225. And obviously that is not in the second quadrant, right? 65.225 is in the first quadrant. So what we'll do here is we'll say x, or we'll do theta. It's going to equal 180 minus that x, or 65.225 degrees, which should be 114.775. And that is your answer. All right, let's move on. So it's given vector with horizontal component of -3 and vertical component of -4. Write a unit vector with the same direction. Okay, so this vector that we have right here, if we were to draw this out, right, it goes to the left 3 and down 4, so it's somewhere down here. And if we were to try to figure out its horizontal and vertical components to find the magnitude, it would be pretty easy, right? Because we've got a -3 and a -4, which means this has got to be a 5 because of the Pythagorean triple, right? 3, 4, 5, right triangle. So our magnitude is 5. Now remember, a unit vector, though, we need a magnitude of 1. So if we want it to go the same direction, right, we're looking for a vector that goes this direction, but would stop down here. right? We want its magnitude to be 1. So if it's going to go the same direction here, you notice that it would form a similar triangle up there. So we just need to scale this back, right? So if you think about it, if this is, if we have -3, -4 for our original, and the magnitude was 5, okay, well, in order to make our magnitude 1, right, we'd have to divide it by 5, which means we need to divide each other part of this by 5 to shrink it up. And so we're going to end up with -3/5, comma, -4/5 when our magnitude is 1. So we've got our horizontal and vertical components. Let's write it in that ij form. We'll write this as -3/5 I minus 4/5 j. That is our unit vector form right there. Okay, so, just one thing to point out there, right? Remember, that means since we have this and this, if we were to take it and do our Pythagorean theorem with those two, right, that should end up equaling 1. Right, if I did the square root of -3/5 squared plus -4/5 squared, right, we would get 9/25 plus 16/25, which is 25/25, which would be the square root of 1, which equals 1. That's why we can say that this works as a unit vector. So the next one's asking if the vector -2/3 I plus 1/3 j is a unit vector. In order to do that, let's think about its horizontal and vertical components. And if we take it and we plug it into our formula, right, -2/3 squared plus 1/3 squared, we'll get 4/9 plus 1/9, which is going to give us the square root of 5/9, which definitely does not equal 1. Therefore, we can say this is not a unit vector, right? Because the magnitude is not equal to 1. All right, last little bit here we've got on bearings. It says bearings typically are used in navigation. It's an angle measured clockwise from due north. Okay, so bearings are used a lot with like aviation, with navigating ships and things there. Everybody has to be on the same page of, when you're measuring there, because we don't want things to collide. So if you think about it in the world, when we use a compass rose, right, when we use that compass rose, or actually there's one down here, right, north is always going to be the same direction for everyone. Okay, if your compass rose works, then, or your compass, that north is always going to be the same direction for everyone. So it's kind of like a universal form of communication. Okay, to make sure that, everything is consistent with all the ships and planes and things that are up in the air. Okay, so it says here that it is that unit typically used in navigation, and its angle is measured clockwise from due north. So when we measure our angles using bearings, instead of using that standard position that's over here, okay, we are actually going to measure from up here. And we're not going to go counterclockwise, we're going to go clockwise. So this would be like 0 degrees, 90 degrees, 180 degrees, 270, and then you're back up here to 360 degrees. But you're rotating around in the clockwise direction. So it says, what is the bearing that represents due east? So when we think about due east, right, we're going from north to due east. Well, if this is 0 degrees, then that's pretty easy. That's 90 degrees. It says Tom heads off towards his aunt's house at a direction which is 10 degrees east of due south. What is Tom's bearing? Well, here's due south down here. Let me change colors. Here's due south down here. So he's 10 degrees to the east of that. So we're talking about probably somewhere over here, right? Because he's 10 degrees from there. So they're asking what is his bearing? Well, if we start here and we go all the way to here, right? So we started at 0 and go all the way around. We're 10 degrees short of halfway. We know that Tom's bearing is going to be 170 degrees. All right, so we just got a couple practice and then we're done. So remember, this is 0 degrees to the top. So if I'm going to measure this one and go all the way from here to here, right? If I know that this is 90 degrees, our answer is just going to come from 90 plus 30, or 120 degrees. The next one, right? Still starting here, we're going to measure around. There's 90, 180, and then we're going 67 past that. So we've got 180 plus 67 is going to give us 247 degrees. And then we've got one more. Okay, so this one, it looks like we start here and it's going all the way around till we get to there. Or you could look at it as if you're going the other direction. If you're going back this way, you've only traveled to 15 degrees. So what we want to say here is, we'd have what? This is 90, 180, 270. So we could say 270 plus 75 degrees should be 345 degrees. Which could also be found by using this part up here, right? If you know that's 15, you could say 360 minus 15 would be 345 degrees. So you get the same thing. All right, if you have questions on any of this, please make sure you mark them down and reach out.